There is one item left in inventory. Two users click buy on it at the same instant. Both requests hit your server. Both queries run against the same database. What happens next depends entirely on how the transactions were written. And getting it wrong is how single item stock ends up sold to two customers, or how a busy checkout page silently corrupts itself in ways nobody notices until a customer complains. This is the episode where MVCC from episode 1 stops being an implementation detail and starts having consequences you can feel. When a transaction begins in Postgres, it takes a snapshot, a frozen view of the database as of that instant, defined by which row versions were live at that moment. Every read that transaction does, no matter how long it lives, sees the world through that snapshot. Other transactions can be writing all around it. Rows can be updated and marked dead by other transactions. This one keeps reading the versions its snapshot considers current. Readers never block writers. Writers never block readers. Everyone gets a consistent view. Which is beautiful, and also exactly why the two buyers problem is dangerous. If both transactions start at almost the same instant, both take snapshots showing stock at 1, both check stock and see 1, both decide yes, we can sell this one, both write stock equals 0 and record a sale, neither transaction ever saw the other's changes because each was reading through its own snapshot. Both commit successfully, neither errors, and you've now sold one item to two customers. MVCC gives you consistent reads. It does not, by itself, prevent two transactions from making decisions on the same data and both committing. To prevent that, you need locks. And this is where a lot of Postgres knowledge gets muddled, because locks are involved silently in operations you didn't realize were locking things. Postgres has locks at several granularities, and they matter in different situations. Row locks are what you typically use to fix the two buyers problem. When a transaction runs select ... for update on a row, Postgres puts a lock on that specific row that says, I intend to update this. Nobody else can update it or lock it until I'm done. The second transaction that tries to select ... for update on the same row simply waits. It doesn't fail, it doesn't see stale data, it just blocks until the first transaction commits or rolls back. Then it acquires the lock, rereads the row, sees stock is now 0, and its application logic, hopefully, refuses to sell. Table locks are heavier and often invisible. Most reads and writes take light table locks that don't conflict with each other. But some operations, a rare few, take an exclusive lock on the entire table. Alter table in most forms is one of them. So is vacuum full from episode 1. So is a regular create index from episode 2. When these run, nothing else can even read the table until they finish. On a busy production table, this is a genuine outage disguised as a routine change. The story that goes with this one deserves telling. You deploy a schema change, alter table users, add column, preferences, JSON B. It should take a fraction of a second. But there's a long-running analytics query on the users table that started 10 minutes ago and hasn't finished. Your alter table sits behind it, waiting for its exclusive lock. Every new query that arrives after your alter table sits behind that, waiting for the lock too. Within seconds, the entire connection pool is queued behind a schema change that hasn't started running yet, blocked by an analytics query that has nothing to do with either. The site is down, and it's not going to recover on its own. You have to kill either the analytics query or the alter. Long transactions are the invisible catalyst here. They don't just hold locks longer, they prevent MVCC's cleanup from advancing. Autovacuum can't reclaim row versions that any live snapshot might still need to see, and that snapshot lives inside the long transaction. A long transaction in production is a bigger source of trouble than most developers realize, and why is my transaction still open is a question worth building alerts around. Now, the last piece, which is really a knob on top of everything above, isolation levels. There are three that matter in Postgres. Read committed is the default and what you almost always run. Each statement in your transaction sees a fresh snapshot as of when that statement started, so you can see other transactions' committed changes appear between one statement and the next, even inside a single transaction. This is loose enough to be efficient and tight enough that most application code is written correctly against it without thinking. Repeatable read locks your snapshot for the whole transaction. Every read, no matter when in the transaction, sees the same view, the one that was current when the transaction began. This is what you want when you're doing multi-step reads that need to be internally consistent, like a report built from 3 joined queries. If a concurrent transaction modifies data your snapshot depended on, Postgres detects the conflict at commit time and returns a serialization failure. Your code has to be prepared to retry. Serializable goes further. Postgres pretends transactions ran one at a time in some order and rejects any that can't be made to fit that pretense. It's the strongest guarantee. No anomalies, no surprises, and it's also the one almost nobody uses in production because retries can be frequent under contention and because read committed plus explicit select for update where it matters is usually good enough. Which is why the correct answer isn't the popular one. So, back to the 2 buyers. The fix is not clever code. It's select stock from items where ID equals 42 for update inside the transaction before checking the value. The first buyer takes the row lock, the second waits. The first commits, releasing the lock and leaving stock at 0. The second acquires the lock, rereads the row, sees stock as 0, and refuses. 2 transactions, 1 item, 1 sale. No code that assumes anything about timing. That's the whole pattern. MVCC gets you consistent reads. Locks, the right ones at the right times, get you correct decisions. Isolation levels tune the trade-off between how much protection the database gives you and how much you have to think about it in your code. Next time, the finale. 1 query traced end to end, from parse to plan to execution to disk to write-ahead log to response, and the honest close on when the answer isn't Postgres at all.